To prove the law of conservation of matter, we are going to intentionally break down a sample of sodium carbonate, converting it entirely into ordinary table salt. We will not be guessing our results. Before we even touch a piece of lab equipment, we will use stoichiometry to mathematically predict the exact final mass of our product. To achieve this level of precision, you need your standard safety gear, a clean porcelain crucible with a lid, and an analytical balance that can accurately weigh items down to the nearest milligram. For our chemical agents, we will be using a specific starting mass of sodium carbonate, a small amount of distilled water, and corrosive 6-molar hydrochloric acid. When we perform the reaction, even a microscopic loss of material will skew the final data. Strict adherence to proper laboratory procedures is the only way to successfully bridge our theoretical math with observable reality. This slide shows the chemical reaction we will be performing. If you look at the bottom net ionic line, you can see how we eliminate the sodium and chloride spectator ions. This leaves the core chemical action, carbonate and hydrogen ions reacting to form water and carbon dioxide gas. Now we transition from the theoretical equation to our physical parameters. For this calculation, we will set our starting mass at exactly 0.689 grams of sodium carbonate. Here we see the dimensional analysis. We start with 0.689 grams of sodium carbonate, use molar masses and our 2-to-1 molar ratio to find an expected yield of 0.760 grams of sodium chloride. We then divide that yield by our initial mass. That gives us a target mass ratio of 1.10. Because the law of definite composition dictates that these compounds always maintain the same proportions, this ratio gives us a fixed mathematical baseline against which we can judge our physical laboratory skills. Step 1 in the physical lab is equipment inspection. Gently tap your porcelain crucible. You are listening for a clear ringing ping sound, which confirms the ceramic has no hairline cracks that could break under heat. Next, set the empty crucible over a Bunsen burner. Heat it gently for about a minute, then fully heat it to a dull red glow. This bakes off any invisible residual moisture that could artificially inflate your starting weight. Turn off the burner, use your tongs to put the cover on, and let it rest on a ceramic tile. You must wait until the crucible cools completely to room temperature before taking your first measurement on the balance. Once cooled, weigh out approximately 0.5 to 0.6 grams of the solid sodium carbonate into the crucible. Record this exact starting mass in your notebook down to the milligram. Establishing a completely dry, structurally sound, and accurately weighed baseline guarantees that our final numbers will reflect actual chemical yield, rather than water weight or equipment failure. Now we begin the conversion. Add about 20 drops of distilled water to dissolve the solid sample, ensuring the carbonate is fully accessible to the acid we are about to introduce. Take your 6-molar hydrochloric acid and add it down the side of the crucible strictly drop by drop. It is highly corrosive, and adding it too quickly will cause a violent reaction that throws material out of the dish. With each drop, you will see rapid effervescence as carbon dioxide gas escapes the liquid. You must wait between drops until all effervescence completely stops. Once there are no more bubbles forming, swirl the mixture gently to make sure everything has reacted. Then add exactly 5 additional drops of acid. This slight excess guarantees total conversion of the reactant. This highly controlled, patient pacing is required to prevent boilover. Keeping every droplet safely inside the crucible secures the physical mass we need to validate our math. Now we move to the evaporation phase. Place the crucible back over moderate heat, with the cover left slightly ajar. This will slowly drive off the water and the excess hydrochloric acid. Listen closely. Any popping sound means the liquid is boiling too vigorously. That popping causes spattering, which results in irreversible product loss and a ruined experiment. To prevent this, hold the Bunsen burner firmly by its base. Regulate the temperature by continuously wafting the flame back and forth under the crucible, applying only enough heat to evaporate the liquid slowly. When the contents appear completely dry and the popping stops, place the cover securely on the crucible and apply strong direct heat for 5 solid minutes. Next, we establish what is called a constant mass. Remove the crucible from the heat, let it cool completely on the tile, and weigh it. Repeat this entire heating, cooling, and weighing cycle until 2 consecutive measurements agree within 5 milligrams. Reaching a constant mass is the physical proof that every last molecule of volatile liquid has been expelled from the crucible, leaving strictly pure, dry sodium chloride behind. To find your final actual yield, subtract the original empty weight of your crucible from that newly established constant mass. This graphic displays the formula for calculating your percent yield. You take your actual physical yield, divide it by the theoretical yield we predicted before the lab began, and multiply by 100. Finally, safely break down your station. Any excess hydrochloric acid must be carefully diluted with plenty of water before being flushed safely down the sink. If your percent yield calculation lands very close to 100%, your physical skills matched the math. By destroying one compound to accurately measure the creation of another, you have proven that the law of conservation of matter is a tangible reality that can be verified with careful, precise measurement.